Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. In prior videos, we built an infinitely scrolling, randomly generated terrain. In this video, I'd like to look at some different ways we could implement revealing that terrain to the player. We're going to look at several variations of fog of war effects. This can easily be layered on top of the infinite scrolling terrain program, but to isolate the effects so we're not wading through a lot of code, I'm going to show them with this very scaled back version. This is called baseprogram.py. You can see the game loop responds to the arrow keys by setting a direction variable, then sends the direction to the player sprite, and then the sprite and the background update and draw. If I run it, you can see that pressing the arrow keys causes the sprite to move, and releasing all the keys causes it to stop. In the code, I also have a background sprite so we can implement our effects. This is a tiled background, but I'm only using one grassy surface tile to simplify the code. There is a two-dimensional integer map which indicates which tile to put at each location in the background surface. So my integer map is a 24 by 32 grid of 2s. 2 is the old index of the grassy terrain tile in my infinite scrolling background, and I just kept that number. It is important to understand how the terrain surface is created to understand the fog of war effect. To create a surface from the terrain map, we have a nested loop. The inner loop draws a row by blitting the tile to the next location on the surface, and the outer loop then advances us down to the next row. When the terrain map contains more than one tile type, we use the next location in the terrain map to get the index of that correct tile to blit. Let's look at fog of war effect number 1, revealing terrain as it's visited. This program is called fog1.py. I'm going to run it, and you can see the terrain starts out mostly black with a revealed area around my sprite. As I move the sprite, more of the terrain is revealed. There's a softening effect around the edge of the fogged area. Let's see how this is done. In this version, I have a field of the background sprite called fog. It's a parallel two-dimensional list of booleans, so true or false values. The list is parallel to the terrain list, so this is exactly the same size as the terrain. If there's a true in a location in the two-dimensional fog list, that means there's fog over the parallel tile in the terrain list. If there's a false, that means there isn't. I've marked all of the code I added to the base program with new code and end new code comments, so you can see more clearly what changes cause this effect. There's nothing different in the player sprite code. Down in the game, after the player is sent the move message and then the update message, I send the unfog message to the background. That's a new message, and it tells the background to unfog the area around the player. Now here I grabbed the player's coordinates from the player sprite's rectangle, which is a public field of the player sprite. I send the player's coordinates to the unfog method so the background can know what part of itself to unfog. Let's look at that unfog method in background. I start by converting the player's x and y coordinates to row and column values by dividing them by the size of a background tile. So a player x coordinate of 52 and a tile width of 25, for example, would put the player just in column 2, 52 flooring division 25. I then loop for an unfogging area that is 2 tiles around the player on all sides, and if any of those tiles are fogged, I unfog them, meaning I set that location in the fog map to false rather than true, and I also set a field called changed to true. That starts out as false. I only want to redraw the background surface if there's been a change. If the player is moving over area that's already been unfogged, we don't want to waste time drawing it all over again. Now I've also added an update method for the background, which is called at the end of the game loop, and in that I check if changed is true, and if it is, the background sends itself a getSurface message, and it sets changed back to false. The getSurface message is where the background surface is initially generated, and where it's regenerated each time part of it is unfogged. Let's take a look. The old part is still there, I loop over the tile map, which in our simplified game is all grass, and I blit each tile to the correct location. However, I'm only blitting if it's not fogged. So I'm checking the fog map there, and if it's not fog, I blit it. There's just no point in wasting time blitting something that's about to be blitted over with fog. But then after that loop, I loop over the fog map, and wherever there's fog, I blit the fog image, which is a new field of the background object. Here's my fog image in Photoshop. It's a PNG. It's larger than a tile, so I calculate where it should blit by taking the difference between the tile and fog tile sizes and dividing by 2. It's dark in the center, and there's a fade to the edges, so when I load it, I send the surface the convert alpha message so it preserves the alpha channel. This will make the tile area completely black, but then there will be that gradient at the edges to soften them some. I do the blitting in 2 passes because of that softening. If I were simply going to have a plain black tile or a terrain tile, I could do this in one loop and either blit the terrain tile or the fog tile. If I try to do it in one loop with the gradient edges on the fog, I get a weird overlapping effect that looks terrible. So 2 passes it is, but I'm only blitting one or the other in either pass. So that's it. Fog of War effect number 1. We add a fog tile and a fog map to our background, as well as a method that will draw either terrain or fog according to the fog map, and a method to defog an area. Now let's look at Fog of War effect number 2, a flashlight effect. This program is called fog2.py, and the first effect we're going to see is very basic, but then we'll look at variations on this basic effect. If I run this program, you can see we have our grassy background, but it's dimmed except for a circle around the player, where we can see the terrain clearly. As the player moves, the circle moves, with areas outside of that circle dimming as the player moves away from them. And the way we achieve this is really quite simple, and is primarily in the background sprite, so let's take a look at that. The main change is in the getSurface method, which, you remember, blits the terrain tiles to the surface. We're back to the basic program now, so we're not blitting any fog. After we blit the tiles, we construct a surface with an alpha channel that is black, but with an alpha value of 180, so it's slightly transparent black. In that, we blit a white, fully transparent circle that is centered around the player. So the primary change that impacts the rest of the program is we need to let the background object know where the player is, so it can create this circle of visibility around the player. You can see that I've added player center as a parameter to this getSurface method. I have added a light radius constant to the background class that is used to determine the radius of that circle. But you can imagine that this could also be a parameter and could be dependent on the kind of light source the player currently has and how much energy it has. For example, we could mimic a torch flickering out or a flashlight losing battery power by reducing that radius over time. So we're creating an overlay for our background that is light around the player and dim everywhere else, and then blitting it over our background surface. The circle is completely transparent, so we see the original terrain exactly as it is when blitted. But where we have the only slightly transparent black, the terrain appears to be in shadow. That is mostly it for this one, except the mechanics that keep it around the player while the player moves. I've added an update method to the background that takes the player's center as a parameter, and update invokes the getSurface method and passes it the player's center coordinate. Down in the main program, I'm passing the player's location to the background initializer, because that is when getSurface is first called, when the background is first created, so we need to send it the player's starting location. In the update and draw section at the bottom of the game loop, we invoke update for the background and pass in the player's location. And again, I get that from the player sprite's rectangle. I like this simple example because it is just a few new lines of code and shows you how we create this light effect, but we can improve it. Fog of War effect number 3 is a directional cone of light, so the player is only looking in the direction they're facing. I've built this on top of effect number 2. I'll run it so you can see. The point of the cone is at the player, and it widens in the direction that the player is facing. So as the player moves in different directions, the cone is always in front of them, lighting the way. For the cone to be directional, not only do we need to know the location of the player, but we also need to know the direction the player is facing. That information isn't actually stored anywhere in this program right now, so I've added a public field to the player class called direction facing. And I set that to player.right in the initializer, because that's the initial direction the player is facing. And I only change it in the move method if the new direction isn't player.stop. This field will always be the direction the player is facing and not whether they're moving or not. We need it to be a direction and not player.stop so we can correctly orient the cone whether the player is moving or standing still. And so I've modified the background initializer and update methods to take the player as a parameter, so we can get both the location and direction from the player directly. And I've added direction to the getSurface method. The getSurface method is where we were previously drawing the circle, and we will now draw a cone. Drawing the cone is a little more involved than drawing a circle because there's no pygame draw method for drawing a cone. That's why I wanted to show you the circle first, so you can see that the overall effect is easy to achieve. And if you don't want to draw a cone programmatically, you can draw it in a graphics program and import it as a surface. But we're going to draw it programmatically. We will use draw polygon. This function works by taking the points of the polygon as a parameter. It then draws lines from the start point to the next point in the list, and from that point to the next point in the list, kind of like a connect the dots that you might have done as a child, until it has connected the last dot to the starting dot. And if we don't pass in a line thickness, it will fill the area. So if we can make a cone-shaped set of dots, then we can use draw polygon to draw them as a white transparent cone over our background. We'll want that cone's point to be at our player, and we'll want it extending out in the direction the player is facing. The starting and ending points are therefore the player's center, so I've started my points list with player center. I'm then going to write a loop to calculate the arc at the end of the cone and add those points to the list. This image illustrates what we're doing. It's a circle, and we imagine our player at the center of the circle facing right, and we'll want to calculate the points on the circle's edge with an arc that is about 1/6 of a circle for our cone. To calculate the xy coordinates for our polygon, we'll use the formula x equals the length of the radius times the cosine of the angle, y equals the length of the radius times the sine of the angle. So what we need to generate is angle increments. Now, the math library's sine and cosine functions work with radians, but I think it's easier to understand this if we use degrees. Maybe not for you. I think in terms of degrees. If I'm thinking in terms of radians, I'm thinking pi over 4, for example, and not 0.78, etc. So I've calculated this both with radians and degrees in the code, but I'm going to talk about it in terms of degrees. I'm generating angle values between -30 and +30 in increments of 3, and passing those to sine and cosine. That's really it. So the first point is the player's center, and then the second point is player's center x plus radius cos -30 player center y plus radius sine -30. And the next one is player center x plus radius cos -27 player center y plus radius sine -27 in increments of 3 all the way through sine and cosine of 30 degrees. Now that works for the player facing right. To adjust for the player facing other directions, we'll add the appropriate angle, 90 for the player facing down, 180 for the player facing to the left, and 270 for the player facing up. Remember, because y increases moving downward, our unit circle angles increase in the clockwise direction rather than the counterclockwise direction. After we've appended those points to the points list, we have pygame draw the polygon over our darkness overlay and blit it over the tiled background. Drop a comment below if you have questions about this code. Now, version 4 is even more fun and built on top of version 3. I'll run it. And hopefully you can see I've added a flicker. This is what I call the flashlight flicker. I'll comment that out and switch it to torch. This is the torch flicker. And this is very, very easy to add. Just before I calculate the coordinates of the cone, I add a slight random element to the radius of the circle and the starting x and y coordinates used to calculate the points. For less variation, as in a flashlight, I generate a random number between -1 and 1. For more variation, as in a torch, I generate a number between -4 and 4 for the radius, and -2 and 2 for the x and y coordinates. I then use these values to calculate all of the points. Each time through the game loop, these random values are recalculated. So each time, there's a good chance the wedge will be just slightly different. This gives it the look that it's flickering. This is my favorite. I love this flickering effect. Now, I did combine the fog number 1 with fog number 4, and here it is. This program is called fog5.py, and all of these programs are in my GitHub repository. There's a link in the description. Here I lightened up the fog to be gray, so you can see where the light is, even if you can't see what's under it until you've been there. But other than the new color for the fog, I've just merged the two techniques. So that is some examples of fog of war effects. I hope you enjoyed it. If you want to chat about it, please drop a comment below. As always, have fun and keep coding.